Today we're going to talk about two-dimensional as well as what happens if there is a translation happens to your structure. So I summarize. I summarize into two equations. So you are required to memorize the first equation. The second equation actually depends on the first equation. Under the conditions that the other ends of the component, the moment is equal to 0, moment-free end, then the other moment can be simplified into this format, where you notice that it's only depending on rotation angle at its own end. It does not rely on the rotation angle from the far end. So if you can memorize or remember this equation, that's fine. If you cannot, you can actually derive that from the first equation very quickly. All right, so with that, next I'm going to give you a two-dimensional structure example. So this is a frame with a concentrate load and the distribute loads. So the property are different. Okay. So first you need to draw the deformation shape and identify degrees of freedoms. So this is a frame under top loads. So most likely the beams here will be deflected downward. So let's start from the right-hand side. So here you are expecting to see some sort of deflection like that. And here you're also expecting to see some deflection like this. But can you imagine that if I deflect it like this, then there will be a compatibility issues there. So it couldn't happen like that because the right angle should preserve. So maybe possible deformation shapes to comply to that is sort of like this. All right, this is just a guess because you actually have to get into calculations to verify the actual deformations. But it's just an indication that you know that this point should undergoing some sort of rotation angle, and the angle, 90-degree angle, should preserved. Okay? And 90-degree angle preserved, so that means that this component is going to be deflected like this, climb end, and here, 90-degree. This is a hinge end. There's no obligations that the slope has to go to 0. So this is possible deformation shape. And you can identify there's an inflation point there. But it could be happening here as well. So it could happen that it's deforming like this, and then bending upward, and then coming downward. So the inflation point should also occurring right there. So whether it's here or there, we don't know. We have to wait until the calculations tell us. All right, so with that, then it's very natural that you model this by one element, one component, 3 component, and 4th component. So you use 4 components to model your structure, and you start to identify the so-called degrees of freedoms. So you can imagine that there will be no rotation angle here, and there will be rotation angle here, not 0. And there will be rotation angle here, not 0. And there will be rotation angle here as well as there. So at the first instinct, it tells you that you should have 4 non-zero degrees of freedoms. Hey, it's too quick to fall asleep. Hello? Yes. Only 5 minutes into the class. All right. Is it because of my tone? Or is it because of the content? Both. All right, so 4 degrees of freedoms. So if you just list out all the equations, eventually you should be expecting to see 4 equations, and you should solve them simultaneously, right? So what do you expect? I want you to have a clear vision before you get into your calculations. So you'll be expecting 1 equilibrium from joint B, 1 equilibrium from joint C, and then another equilibrium joint D and joint E. So can you see that? That's how you formulate your equations coming from the joints. Cool? So 4 equations, 4 unknown. Now, if you remember or recall that we have such equations, if the far end moment is equal to 0, then the other end's moment can be expressed by its own rotation angle, but not the other rotation angles. So if that is the case, if we utilize the second equation there, then write the moments as a function of its own rotation angle, but not this. And write this moment in terms of its own rotation angle, but not this. Then you will see that you will only end up with 2 unknowns, which is theta B, theta C, and not theta D and not theta E. So you'll come out with 2 equations solving for 2 unknowns. So obviously, if you remember or if you know how to derive this, you actually can avoid solving a simultaneous equations of 4 and only solve for 2. So this is what I'm going to do. So I'm going to follow the procedures one by one. So for AB component, rotation angle theta A is equal to 0, so only 1 time theta B. No rigid body rotations, no fixed end moment because no external loads. MBA two times theta B, and that's it. And then you go to BC components. Two times theta B, 1 times theta C. Is there any rigid body rotations? No. No rigid body rotations, but you do have a fixed end moment. So this is a, oh, I didn't give you the dimensions. Sorry. Dimensions should be given. All right. So it's a mid-span concentrate force. So the formula for that is PL over 8. PL over 8. So let me just keep that temporarily. You know how to calculate. So this is PL over 8. The other one. Two times theta C, 1 times theta B. And then fixed moment CB. So this one should be minus PL over 8. So that's BC. Next. So this one, next is this one and that one. And I'm going to use the second formula. You don't have to, but if you can identify that beforehand, that's supposed to help you in calculations. So theta I is theta C. And the rigid body rotation is equal to 0. So that's it. And any fixed end moment, no loading, so no fixed end moment. So that's CD, and MDC is equal to 0 by default. This pair of equations, you can just follow the original ones, but you will end up with simultaneous equation though. What? Any mistake? Fine. All right. Last one, CE. There. So CE, I'm going to use these 3 EI equations. So theta C, rigid body rotation equal to 0, but I do have fixed end moment due to loading. All right. And then the other one is, of course, equal to 0. All right, so I'm just write out the slope deflection equation for each component. Next is equilibrium. Okay, join equilibriums now. Join equilibriums. Join B. So I pick up this one and this one, sum up, equal to 0. And join C. So I pick up this one, and this one, sum up, equal to 0. All right, 2 equations. So you look into the equations, there are only 2 unknowns, which are rotation B and rotation C. So you can solve for these 2 unknowns from the 2 equations. All right, so I leave it to you. I'll just give you the solutions. So theta B here we go. We Got it? Okay, is there any question? Huh? Dimensions of the. Yeah, thank you, thank you. Thank you. Missed it. And I also need to give you the Young's modulus. So any other question? What? Mấy cái lại cái. What is saying? All right. So negative means what? Clockwise. So the rotation angle is clockwise, both of them. So this is clockwise and this is clockwise. So it's indicating that the deformation shapes that I drew is correct. Okay? So you'll be expecting to see an inflation point between B and C. All right, so can you follow up? You take this two value and start to plug them in to the M moments. So plug them in, substituting properties, geometry properties of the materials. Then you will start to get the N moments value. So MAB is MBA MBC CB CD and CE. All right. So I just take these, substitute them back in one by one. So I get the N moments. Also, if you are interested in finding out this rotation angle and that rotation angle, how to find them? Anybody know how to find them? Well, these two angles can be found from these equations. So if you expand our equations, it's 2EI CD LCD 2 theta D 1 theta C, no rigid body rotations and no fixed moment. So this should be equal to 0. So it tells you that theta D is minus 0.5 theta C. Right? So you have theta C. So you have theta D. So theta D should be positive number, right? Negative, negative, so it should be positive. So indicating that this is counterclockwise rotation. So similarly, you can get rotation angle E from that equation. So you can solve all the parameters or degrees of freedoms if you wish to. Finally, you should be able to plot the shear force and bending moment diagrams. So let me just give you. So this is what we are getting. And what can you go from here? So we are getting n moments. MAB is minus. Minus means clockwise. So here, clockwise, bending moment. MBA is negative, again, clockwise. Now, when I say clockwise or counterclockwise, I always refer to components. Shh, be careful. There's a difference between components and joints. So when I say clockwise, counterclockwise, I always refer them to components. Because according to action reactions, then you know that this clockwise is going to become counterclockwise at the joint. So don't get yourself confused. All right, so that's AB. And then BC, positive means what? Counterclockwise. Counterclockwise. So action reactions, that's why you see the balance between the two. Right? So that's MBC. And MCB is right here. And this component is positive. Positive is counterclockwise. Action reaction. And next is CD, from C to D. So here, this component, CD is positive. Positive is counterclockwise. All right? And this is equal to 0. The last one is CE, is negative. Negative on this component means that it's clockwise. So action reactions clockwise. 55.9. So you see that at the joint, there's an equilibrium there. And moment equal to 0 there. So finish up the analysis. You just go to each one of the components and then obtain the shear force. So you come over here, calculate. Okay, equilibriums. So they are performed at the elements level. And here, come over here, do equilibriums on the components. Oh, there's an external force, don't forget. There's an external force of 30. And there's an external force of distributed loads, 50. So, equilibriums. Finishing up. So you finish up all the analysis, action reactions, balance. So this is 79. They should have a shear force of 1.4. 1.4. What else do we miss? Is there any more numbers that we missed? You should get this number. Oh, I think this is wrong. Sorry, this should be action reactions 25, 25. Okay, so I think you should have enough information to plot shear force bending moment diagrams now. And you'll be asked to plot the moment at the tensile side. So this is just local equilibrium calculations. Okay. Cool. So next, let's take a look at what happens if we have translations in addition to rotation angle. Any questions about this particular example? Okay, can I erase now? All right, let's try this out. See how we handle degrees of freedoms involving translation. So apparently, I want you to model the structure using two components, one vertical, one horizontal. But because this is clamp, this is rolling support, so there's a horizontal force. Also, even without the horizontal force, because the structure is not symmetrical, so you will be expecting to see some translation even though there's no horizontal force. So imagine that if I take away this force, apply loading like that, can the beams translate? The answer is yes. The beam will translate because the structure is not symmetrical. So there's no reason why the structure will not translate if the loading is applied. Okay, so we'll be expecting to see deformations, translations. So can you imagine the translation or the deformation shape of the structures? So point B is going to be moving. Now, whether you will be able to draw the deformation shapes without calculation is an indication of whether you understand structure knowledge. So that is very important. So in the exam, I always ask you to draw deformation shape as much as possible. Okay? So, this point, translation. Now, in principle, we say that we are going to adopt actually inextensible assumption because actual rigidity is always much bigger than the flexural rigidity. So what I mean is at this point, it takes much effort to compress this point actually than to translate that. So it's a very common assumption that we assume the components are not extending actually or compressed actually. So in other words, this point is going to move in a circular fashion. In a circular fashion. Also, in our analysis, we always assume that it's a small deformations, very, very small deformations. If the deformation becomes significant, then we cannot use a linear theories to cover that. We have to use a nonlinear theories to cover. So this is the first in structure analysis course for you. We always assume that this is a linear structure behavior. So deformation is kind of restricted to a very small values. So in other words, this point is going to be restricted to move in the perpendicular directions. Okay, because of a small deformations and actually inextensible assumptions. All right, so imagine that this point now is moved to this point. And this deformation, I call it delta. So this point, point C, again, is going to move horizontally. But how much? Because we say that we are going to use actually inextensible assumptions, so this component also cannot be extended or compressed. So in other words, if this point moves delta to the right, this point also moves delta to the right. That's complying with the actually inextensible assumption. Okay, good. Of course, in reality, you will see slight difference between the two because actually it does compress or it does elongate it. The amount is very, very small in comparison to the calculation, the deformation that you're going to get. It's going to be a very, very small. So we kind of ignore that in the linear structure analysis. All right, so point C is going to move to these locations. And there's a vertical force, so you're expecting these components to deflect sort of like that. And 90 degree remains 90 degrees, so it's sort of more like this kind of deformation that we are looking at. All right? Cool? So this is the deformation shape. Now with that, we can start our analysis. So there will be 2 degrees of freedom, theta B, theta C, so expecting to see 2 degrees of freedom, theta B and theta C. If you can remember this, the second equations I put down, so it can further reduce the degrees of freedom to 1. But this is not so complicated. And just in case that you don't remember the second equations, so that's fine. As long as you know the slope deflection equations. So no problems. Oh, I'm sorry, not 2 degrees. There's a translation as well. So they should have 3 degrees. 1, 2, and 3. 3 degrees. So you need the 3 equations. So joint equilibriums, 2 equations. Where is the third equation coming from? Oh, that's the key. Where is the third equation coming from? All right, so let's try. So here's a loading, 60. Here's a loading, distribute load. N moment, this is MAB. MAB is 2EI over L theta B. There's a rigid body rotations. So rigid body rotation is connecting the deformed shapes, the ends of the deformed shape. And then measure this. This is called rigid body rotation angle. And again, it's positive if it's counterclockwise. Negative is clockwise. So this apparently is clockwise. So it's negative rigid body rotations. So rigid body rotation is delta divided by the length. So it should be 3 times delta divided by length of 10. All right. So the other ends called MBA, 2EI over L, 2 theta B, no theta A, rigid body rotations, 3 times rigid body rotations, and then no fixed end moments. For BC components, this is M BC 2EI over L 2 theta B 1 theta C, no rigid body rotations and fixed end moments. So UDL is WL squared over 12. And finally, this end, this is MCB, 2EI over L, 2 theta C, 1 theta B, no rigid body rotations, fixed end moment, CB. Okay. So apparently we have 3 unknowns. We need to come up with 3 equations. The first equation comes up very quickly. MCB equal to 0. That's the first equation. The second equation is a joint equilibrium here and here. So joint equilibriums tell us that MBA plus MBC equal to 0. That'll be your second equation. All right, so now where is the third equation coming from? Because we have 3 unknowns, we need the third one. The third one is actually coming out from global equilibriums. What is global equilibriums? Let me show you. Moments. So you can obtain shear force. So this shear force I call FAB. It's going to be based on component equilibrium MAB plus MBA divided by the length from local equilibriums. I come over here, take a moment equilibriums. I can find out that force. That force is this force. Okay? And according to global equilibriums, this force should be equal to 60. So here. That's the third equation coming out from global equilibrium. Okay? Conceptually, fine. The rest is just mathematical calculations. If you understand these, then the detailed calculation is pretty straightforward. All right, so I'll let you chew on it for 2 minutes. Let me know if you have any questions. Is there any part that you don't understand? You need me to explain further? Yes? This? Y is plus, not minus, right? Now, original equation is what? Minus? Minus, right? Minus 3 times rigid body rotation angle, right? But this rigid body rotation angle is clockwise, so that becomes positive. Okay, any further questions on this? Concept is more important, or concept is the first step to help you understand. And as I say, the rest is mathematical calculations. You have 3 unknowns, 3 equations, solve for 3 equations, and then substitute back into the moment equations, and that's it, right? That complete the slope deflection approach, and the rest is just equilibriums. Okay, any further questions on this? Okay, remember this. Joint equilibrium, if joint equilibrium is not sufficient, then you go to global equilibrium. Now, where do you get the equation from global equilibrium? Then most likely depends on the calculations of shear force. So you go to shear force calculation and come out with a global equilibrium. Okay, so just finishing this up. You can go home and verify this. Okay. Sort of finishing up. So it's telling you that theta b is negative, which means it's clockwise. Theta c is positive, which means it's counterclockwise. So this is clockwise, and this is counterclockwise. And delta is positive, which means that it's going along the direction that you assume. All right? If you obtain delta, which is negative, that means that it's going against your direction. But it's positive, so it's along the direction that you assume. So this is a correct deformation shape for the structure. All right, so after that, things become very routine. You just take all 3 of them, start to back substituting each one of the end moments, and then finishing up with local equilibrium, calculating shear force, and then you'll be able to plot shear force bending moment diagrams. Okay. Cool. Now, it's not a requirement that you guess your deformation shape correctly in your first attempt. It's not required that you guess the deformation shapes correctly. For instance, well, next I'll show you. It's kind of hard to decide which way it's going. But it doesn't really matter because your calculation will tell you. So if you assume the deformation that way, but it turns out to be this way, that's fine. The solution will tell you which way it should be. Okay, if no questions, next is this. All right, so let's look at this one. So this course is actually very important because not only you start to accumulate your structure, knowledge, and common sense, although eventually when you go to a company, they might want you to use some sort of computer software to analyze structure behavior. But this is actually the very first course for you to start to accumulate this kind of knowledge. So you will need to know very, very well moment, curvature, moment distributions, like how do you plot the proper deformation shapes, etc. So those are very, very important structure knowledge or structure intuitions that you must have. So next year, this year, no, you'll be graduating in 2016, right? Supposedly you don't fail this course. If you so ideally, you will be graduating in 2016. So I bet you, before you graduate, if you are thinking about working in a structure firm or structure divisions of a company, you will need to come back to visit the course material that I taught here. So hold on to those PowerPoint files and hold on to your own notes, because a lot of companies actually, the criteria for you to get interviewed is you can pass some sort of written test, and quite often they will give you this kind of analysis as your written test. So they will ask you to plot moment diagrams, shear force diagrams, deformation shapes. So before you start to apply and then get interviewed, you need to pass those tests. As a matter of fact, last week we have the congregations, right? There's one graduate came back and tell me that she got accepted to a company, and after a few months, the director decided to ask him to do a structural analysis test after a few months of work. Well, maybe he didn't do very well, so, so they want to verify whether he knows the structure very well. So yeah, eventually you will be using computer software to do these kind of analysis. But your instinct and engineering sense is still very important. All right, so instinct like this. First of all, you need to know how does this structure deform under this kind of loading. So can you imagine the deformation shape? Do you think that the top beam is going to translate horizontally? Although there's no horizontal force, do you think that it's going to translate horizontally? Yes or no? Yes, tick. Blue tick. Yellow tick or blue tick? All right, so now if this is a symmetrical structure, if I have a loading like this, the loading is symmetrical, right? Structure is symmetrical. So the deformation has to be symmetrical. No choice. Structure symmetrical, loading symmetrical, deformation has to be symmetrical. So if that is the conditions, then you won't be seeing the structure moving horizontally, because one is moved to the right-hand side, it's not symmetrical. So you can anticipate that the deformation shape of the structure is going to look something like this without any questions. Symmetrical. That's a concept we try to introduce to you in that particular chapter, symmetrical, anti-symmetrical concept. Right? All right, so now the question is, if the loading is not symmetrical, then what happened? If this is a symmetrical structure, but unfortunately the loading is not symmetrical, so what do you expect? There's no restriction saying that the deformation has to be symmetrical, right? Because the loading is not symmetrical already. So it could happen that this top portion start to translate. But translate to the left or translate to the right? What do you think? Right? Move to the right or move to the left? All right. Who vote for right? Okay, at least there's one. Oh, two. Right. Who votes to the left? Okay. So why don't we do this? I want you to go back and analyze this and let me know next time. Okay? Is it going to the left or to the right? Let's say to the right. It should be like this. That's to the right. And to the left is the other way. It's quite interesting, is it? Okay. But if you don't have such an instinct, it's fine. But at least you should know that it's going to translate now, because the loading is not symmetrical, although the structure is symmetrical. Okay? Now, let me just analyze on this and let you know we start to develop our instinct or concepts. So this structure apparently is not symmetrical, loading is not symmetrical, there's no obligations that the deformation has to be symmetrical. So it could go to the left or go to the right, we don't know, but we know it's going to move. All right? So let's say that arbitrarily, I say this point now move to the left. I'm not sure. I need to calculate to verify. That's what you should do as well. You try to calculate and verify your instinct. All right, so this point now move with this amount called delta. Because actually in extensible assumptions, then this point D is going to move with the same amount, delta. So if that is the case, so I'm going to expect to see the deformation shapes like this. And angle preserved. So that is a deformation shape. Y is horizontal, just like I mentioned. It's along the tangential direction because of actually inextensible assumption. Okay, cool. Now, I start to use a slope deflection approach very quickly. So go to the joint. I'm expecting to see rotation angle, and then translation. So there are three unknowns. So I'm going to come up with one joint equilibrium, two joint equilibrium, so two equations. And the third equation, again, is going to come out from global equilibriums. So let's go for that. So this is joint C. Now as you start to get familiar, so I'm going to skip some sort of details. So remember that this M moments applies to components. So the clockwise is actually corresponding to positive in the components like that. Right? So MCA. That's MCA. So this is MCD. Okay. These are the two M moments meeting at joint C. And then I go to the other side. This is joint D. So I'm going to see moments. So this moment is M. This M dB that's MdB, and this is MdC. All right. So going to the components. You write down the components. So you should have another expressions of moment here, MAC, and another expressions of MBD. So doing shear force balancing. Get that? This is the shear force. And you should have another shear force here. Okay. So that shear force is going to act here and there. So let's call this shear force A. This is shear force B. So this is A, this is B. Okay, equilibriums come out. FA plus FB equal to 0. So you substitute these in here, plus the joint equilibriums. And then here, this joint equilibrium. So I'm showing you the 3 equations that you can use to solve for the 3 unknowns. Okay, that is mathematically sufficient now. 1, 2, 3. Okay, good, cool. Now let me show you the solutions. Please go home and verify this. All right, that's the solutions for rotation angle C, D, and translation delta. So let's look at the solution and try to adjust or correct our deformation shape. So rotation angle at C is negative. Negative means that it's clockwise. This is counterclockwise. So this is not correct. So it should be deflecting clockwise like that. Theta D is positive. Positive means that it's counterclockwise. So this is counterclockwise, so this is fine. Okay. Translation positive means that it's along the directions that we assume. So that's fine. So as a result, the deformation shapes looks like this. All right, so that's the deformation shape, correct deformation shape. Okay, so your answer will tell you the correct deformation shape once you obtain. Okay, any questions? you can try to assume a different deformation shapes and see what the answer tells you. Right? That's a way to practice. Okay, let's see how we can handle this kind of problems. All right, is there any questions about that example? Okay, if not, let me try to wrap up this chapter. So what happens if I have an inclined component, which is not like 90 degrees? So something like that. Now, before I tell you what to do, let me ask you these questions. This is horizontal support, right? So is this support the same as this support? Are they the same? Yes? Oh, no. Yes? Oh, no. Yes? Yes? No? No? Don't know? Don't care? Well, so the answer is, of course, depends on who you are. Who you are. Thank you. If you are not a structure engineer, then you will say they are not the same. Because they are not the same. They don't look the same. But if you are a structure engineer, they are the same. Why? Why? So the results, if I plot it like that or plot it like this, the result is exactly identical. Structurally, it's exactly identical. There's no difference. Structurally, there's no difference because there are three unknown forces associated with this. 1, 2, 3, right? So if you take a look at this support, there is a force here, there, and here. So they are called equivalent force. They are equivalent force. So you can obtain from one set to another through equivalent force. So structurally, they are the same. Now, if I ask you these questions, now, would your answer be more confirmed now? If I do it, or if I do it like this, Okay, same orientations. So do you think they are the same? Yes? No? Don't know? Don't care. well, this is pretty obvious. It's not going to be the same. They are not the same. Why? Because this is going to move along this directions, but this is going to move along that directions. The motionists already tell you that it's not going to be the same. All right, so be careful. This is more like an instinct. All right, so what I'm going to do here is not, I'm going to show you the deformation shape. I'm going to show you the deformation shapes. You need to draw them correctly, otherwise your analysis will be wrong. This is more challenging, of course, because now you don't have 90-degree orientations. So you need to have this concept of actually inextensible concepts very, very well. All right, so let's start. How do I draw the deformation shape? I call this A, B, C, and D. All right, this is fixed N. So this point C, where is going to go? Where does this point go? It's going to be along the tangential direction or perpendicular directions to your components orientation. So perpendicular directions, 90 degrees. So either going you're loading. Cool? That's the first thing you need to make it right. Otherwise your analysis is completely wrong. All right. This point, again, it's going to move along the perpendicular directions to your components, 90 degrees. So either that or this. Cool? So this point, imagine this point is going to move here. Let's say this point, can it move here? Can it come over here? No. If it moved to this location, that means that this component is going to be compressed. The length of the component is going to be shortened. And we say that it's actually inextensible. So that kind of violates the actually inextensible assumptions. So the only way to follow the actually inextensible assumptions is to let this point move to this location. So this point move to this location, that point move to that location. All right? Also, we need to comply assumptions, actually inextensible assumptions. So that means that this point, if this point move with this amount, delta, this point should also move with this amount, delta. We are assuming a very, very small deformations. So this point, of course, I exaggerate, but it's going to move very close, very small amount. So this translation and that translation has to be the same in order to comply to actually inextensible assumption for that component. All right, as a result, here is the deformation shapes. So this imagines I'm going to have rotations, and I'm going to have rotations somehow like that. So here is so it looks something like that. If I have a loading applied, of course, the detail, the exact deformation shape has to be confirmed once you obtain rotation angle and translation. Then you can come back and correct your deformation shapes. But this is a potential deformation shape. So from there, I just want to show you that our unknowns are rotation angle and rigid body rotations, right? We have rotation angle and rigid body rotation. So if this is your case, is your problems, then you'll be expecting to see rotation angle C, rotation angle D, two unknowns, plus this translations. This translation is going to get in to your rigid body rotation angle because this beta 1 is here. This is beta 1. So this is going to be the, delta cosine beta 1. So as a result, your rigid body rotation